You've seen how to use parallel invoke to run a set of actions that will be distributed across the different cores and threads available on your system. This is to effectively deal with chunks of data to process them in smaller pieces. Instead of using parallel invoke, we are now going to explore two different approaches. The code that we've written so far isn't really flexible enough. If we add more stock identifiers that we'd like to process, doing so would require us to change the code. Obviously, this isn't dynamic enough, and the code we've written so far isn't really production ready. How about we use a loop to iterate the stocks instead of manually creating these actions with anonymous methods? Refactoring this code to use a for each or a for loop will be pretty easy. We've got a lot of similar code snippets here, which should indicate that we can make this a lot prettier. The parallel class exposes a method that allows us to define a for each loop. This method has a bunch of overloads that will allow us to introduce custom behavior. What these all share is that they expect a source of elements to iterate, as well as the body that will execute for each element. This sounds, and in fact is, very similar to how a normal for each loop behaves. The main difference is that it will automatically scale the work across all the available resources on your system. This means if we have hundreds of elements that we could process in parallel, the runtime will figure out the most suitable way to distribute this work. Hence, it will compute the degree of parallelism. Then it will run the body for each element in parallel. We don't have to worry about threads or the task. This method call is solving all of that under the hoods. This is what makes it a very powerful library. The first parameter that is passed to the for each loop is the source. This could be any IEnumerable. We can pass the dictionary that represents the search result of stocks. The second parameter is the body for the for each loop. This is represented as an action, and we could point this to a method as well as long as it matches the signature. But we're going to use an anonymous method. The method or action will receive a parameter. Can you guess what this parameter will contain? It'll of course contain the value we're currently going to process in that iteration, much like the element in the body of a for each loop. The body of the for each loop, or rather the body of the anonymous method, will now just contain somewhat the same code we had in each anonymous action that we passed to parallel invoke. We'll perform the calculation for that stock, then the result of that calculation is added to the thread safe collection, which we can later use to update the UI. We can now get rid of the previous code that uses parallel invoke. This is, in my opinion, a much cleaner and easier to read solution. As you run this, the application behaves just as it did when we used parallel invoke, which is providing a really nice user experience. The computation was done as fast as possible using all the available resources. If we now extend the list of stocks to process, it would just work without having to do anything extra. We've also continued to use both the asynchronous as well as parallel principles together, as we've now wrapped the parallel for each call in a task.run. A funny side note is that on my computer, this is not even utilizing all my available cores. As this list grows larger with more items, the difference between the parallel and non-parallel versions will therefore be a lot different. We rather easily converted this to use a parallel for each loop. Just as with parallel invoke, you can pass parallel options, which would contain a configuration for the degree of parallelism or the cancellation token. You can experiment with the degree of parallelism and change the amount of concurrent tasks that we are allowed to use with parallel for each. This makes it very flexible, and with very minimum effort, we did make the application a lot better. Parallel for each as well as parallel for both return something called a parallel loop result. This return value will tell you if the execution completed successfully. Completing successfully means that the loop ran to completion and that it didn't receive a request to end prematurely. Ending prematurely means that an iteration requested the loop to break or stop. The parallel loop result also contains a property for the lowest break iteration. This is just relevant if you're using parallel for, as it represents the lowest index of where a break was called. You could have multiple parallel operations that have already started. When one of them requests to break, it won't automatically stop the others from running. Let's look at how we can break out of a loop. You can't simply use the break keyword like you do for a normal loop. You must take a slightly different approach. You also need to make sure that consecutive operations won't start executing once you've requested a break. This is just another way of saying that we don't want to start the rest of the parallel operations that are waiting to be processed. The action that represents the loop body accepts a second parameter of type parallel loop state. This parameter is a representation of the loop state, which will provide a way to communicate that we'd like to, for instance, break or stop the loop. You can call the method state.break, and that means it will only cease the executions of iterations beyond the lowest iteration index. What is also important is that it's breaking at the system's earliest convenience. Let's assume that you have 100 elements to process in parallel. If you request to break at the index 50, that means all the iterations with a lower index than 50 should still run even if they have not yet started. Anything above the index 50 will not be started. This is why the lowest break iteration is particularly interesting. There's another method available on the parallel loop state that would allow you to cease the execution of further iterations. This method is called stop. If you call stop, it will communicate that it should cease the execution of the parallel loop at the system's earliest convenience. If you call stop, other already executing iterations will be able to check the state property to see if isStopped is set to true, and could then handle that and exit gracefully. Let's break when we find one of the stocks that we know are available. We also have to make sure that the code beneath this won't execute. Calling state.break is just a normal method call. So either we wrap the code below in an else block, or we'll just return. It won't automatically exit the current context. Before you run the application, make sure that you set a rather low degree of parallelism and add a breakpoint. As you search for the stocks, it will hit the breakpoint, and you can see that the loop result has the isCompleted property set to false. This is because the loop didn't in fact complete, it detected a break. As we are still using the parallel for each loop, the lowest break iteration property is of no value to us. What may come as a surprise is that it proceeds to run the next parallel operation as well, and then finally stops. This is because it's breaking at the earliest convenience. You can change the degree of parallelism to 1 and then break on the first stock. Doing so gives you a little bit of a different result. Can we make this better? Could we detect that a break has been requested and gracefully handle that? Definitely, there's a way to check if another iteration has requested to break. The state parameter passed to the loop body has a property called shouldExitCurrentIteration. This will be set to false unless another iteration has requested to break. If the previous iteration requested a break, it will be set to true. Now, the result is a little bit different, and probably more so in line with what you might have expected. This will cease the execution of the iteration that have not yet been executed. We've been using the parallel for each, but using a parallel for loop is equally simple. It also provides the same functionality and configuration capabilities. If you know how to use the parallel for each loop, you'll definitely feel right at home with a parallel for loop. Just like a normal for loop, it provides a way to iterate from one index to another. the from index is an inclusive number, while the to one is exclusive. That means if we'd like to iterate from 0 to and including the index 9, we'd construct a parallel for loop that states 0 and 10. Obviously, there's a loop body, just like the parallel for each loop. This provides the index instead of the item, as we saw with the for each loop, as well as the state. I'd suggest that you experiment with this loop, and we'll use it more further down in this course. At a first glance, though, it's very similar to how you'd use the parallel for each, like we've just experimented with. Not only is this very powerful, it's also very flexible, and it's built on top of the task parallel library, which we've seen is extremely powerful, and it allows us to do simultaneous processing. All of this illustrates how easy it is for us to introduce a parallel iteration in an application to process lots of data. We've still got a lot of topics to cover, such as blocking, deadlocking, shared variables, canceling parallel operations, and parallel link.